Alright, welcome to another AQA AS chemistry video. Today I'm going to be doing a video on intermolecular forces. Alright, so types, let's get straight into it. Types of intermolecular forces. Intermolecular forces operate between all types of molecules. The clue is in the name, inter, which means between, and molecular, which means molecules, which means, so therefore, intermolecular forces just means forces between molecules. And they're generally much weaker than they are just weaker than intramolecular forces. And we're going to look at three types of intermolecular forces. The first one being induced dipole-dipole interactions. So these are the weakest intermolecular force, intermolecular interactions. It could be called forces or interactions, but it doesn't really matter. The same thing. So they're the induced dipole-dipole intermolecular forces are the weakest type of intermolecular force. Permanent dipole-dipole interactions. So these are stronger than induced dipole-dipole interactions, but weaker than hydrogen bonds. And hydrogen bonds, these are the strongest form of intermolecular forces we should consider. They're still much weaker than intramolecular forces, for example, covalent bonds. Covalent bonds are the strongest. So I just want to clear something up because a lot of people get this wrong and they get really confused by this. Covalent bonds are the strongest bonds because they're considered to be intramolecular. Hydrogen bonds are the strongest type of intermolecular force. Because people say, oh, but I thought intermolecular force is the strongest type of bond. It is, but covalent bonds are stronger because hydrogen bonds is only intermolecular. Covalent bonds are intramolecular. They're considered to be intramolecular. So the hydrogen bonds are the strongest type of intermolecular force. Covalent bonds are the strongest type of intramolecular force. So everyone gets confused. They're saying, why is sometimes my teacher saying it's the strongest type of bond, but covalent bonds are stronger? No. Hydrogen bonding is the strongest type of intermolecular force, but overall intermolecular forces are weaker than intramolecular forces. But hydrogen bonds is the strongest type of intermolecular force. But of course, covalent bonding is the strongest type of intramolecular force. Hopefully that makes sense. If it doesn't, just leave a comment on the video. And the next is induced dipole-dipole interactions. Induced dipole-dipole interactions are also known as Van der Waals or London forces. So I'm going to go straight into. I'm going to go through all of these right now. So I've made this video specifically for each type of section. So induced dipole-dipole, permanent dipole, and hydrogen bond. So, right. So induced dipole-dipole interactions. Right. So induced dipole-dipole interactions are also known as Van der Waals or sometimes called London forces, but just use Van der Waals. That's the one that AQA tend to focus on. And they're formed from temporary dipoles. So temporary dipoles are when the electron clouds around molecules are constantly in motion. So one moment all the electron density can be on one side of the molecule. The next one can be somewhere totally different. And I talked about electron clouds on my previous video or 2 videos ago. So I'll leave the link in the description to that video. And this is called a temporary dipole when this happens. So this is called a temporary dipole. There's a partial charge, but they change very rapidly. They don't stay. The force isn't constant. It's not constant. It's in the name. Temporary dipole, induced dipole-dipole interaction. It's not like a permanent dipole where the bond is stable. It stays within place. All the electrons are constantly within one region. Whereas with induced dipole-dipole, the electrons can be the electron density can be on one side of the molecule and then completely on the other side. The electron could be anywhere within this cloud. Think of the electrons as being an electron cloud. It's, anywhere here, and that's not very stable. Whereas with your permanent dipoles, they're a bit more, they're more fixed in one position. They're not necessarily at one point, but they're more constant roughly in one position. So they're generally much stronger because electron density isn't being flown from left to right, from right to left. So that's what makes this bond kind of stronger. So that's what makes permanent dipoles stronger, but that's what makes the permanent dipoles, which is where I'm gonna go to next, stronger. But these temporary dipoles, that's what makes them weaker because the electron isn't constant in one position. It's kind of anywhere within that electron cloud. It's not a strong bond. It's not a strong attraction to one specific position. Induced dipoles. So if one molecule has a temporary dipole, its partial charge will exert a force on nearby molecules, right? The partial charge of one molecule can push away the electrons in another or attract them towards it. So when you have a partial charge, it will exert a force on a nearby molecule. So if this is a partially positive, if this is a partially negative charge or a partial negative charge, it will push the electrons away from the molecule. That's kind of what's going on here. So if it's partial negative, if this is a partial negative charge on this atom here, for example, on this carbon here, it pushes the electrons away from it. And this is done with compounds that generally aren't that electronegative. That's so induced dipole-dipole interactions happen with generally regarded as non-polar intermolecular forces. So if it's between, right, let's say it's between, let's just call this an propane, right? And this is between two propanes, right? I should have got like a, can I get that here? No, I can't. All right. But the point being, it says between two, it's this, the intermolecular forces are between molecules, right? So the covalent bonds will be the intramolecular forces between propane, and let's say this is the bond, the intermolecular force that's between two propane molecules, right? Because there's not a severe difference between the carbon-carbon bonds, well, actually, it'd be exactly the same. There'll be a period where one carbon has a, there'll be a period where one carbon is more partially positive, and then one carbon is more partially negative, and they're constantly switched around, right? When it's more partially negative, it'll push the electrons away from it. When it's more partially positive, it'll push the electrons towards it. And if one's electron negative, one will always be partially positive. That's just how it works, right? And that's the force that they're doing. This repulsion force, repulsion and attraction force. So this means that temporary dipoles will induce dipoles in nearby molecules. Once a dipole has been induced, it will be attracted to the initial dipole. So this is called an induced dipole interaction, or a van der Waals force. Strength. Van der Waals forces are not the same strength. The strength depends on the number of electrons in a molecule. Molecules with lots of electrons will have a much stronger van der Waals force, or van der Waals forces. This is because they will have a larger fluctuation in electron density, and this leads to a larger temporary dipole and stronger dipole-dipole interaction. For example, in I2, as I said before, if you go down group 7, there's more electrons, and it's just the same principle here where there's more electrons, there's more of that fluctuation between the electron density, and you're forming more stronger, because there's more electrons present, you're going to form a stronger van der Waals intermolecular force compared to when there's less electrons. That's one thing you need to understand. So as you go as you go down group 2, so as you go down group 7, you'll increase the number of electrons, more electron shells, but there's more electrons in general, and therefore your the type of intermolecular, the type of force is same. It's still van der Waals intermolecular force, but there's more electrons. There's a stronger induced dipole-dipole interaction, and therefore stronger van der Waals intermolecular forces, because there's a large fluctuation in electron density, right? And that's why as you go down group 7, you can see that because there's more van der Waals intermolecular forces, the state of matter changes from being gas, which is bromine and chlorine, fluorine and chlorine, to being more liquid and bromine. And then you see iodine is generally at room temperature is a solid, right? If there's more electrons here, there's still more of them. There's more of them going to be passing over one another. So that's one thing you need to understand. So the number of electrons will also affect the strength of that van der Waals intermolecular force. They're constantly fluctuating in between that gap there. This is the intermolecular force. This would be the intramolecular force. Alright, so now I'm going to go on to permanent dipole-dipole interactions. Permanent dipole-dipole interactions exist between two permanently polar molecules. Permanent dipoles. Permanent dipoles have a partially negative on one side and a partially positive on the other side. The partially positive of one molecule will attract the partially negative of another molecule. That's kind of understanding the laws of attraction, not difficult to understand. And this means that the molecules will line up throughout liquid or solid in this fashion. Permanent dipole-dipole forces are the second strongest molecular interaction. So, polar molecules, right? So, permanent dipole-dipole interactions are only possible in polar molecules that contain a permanent dipole. So, they are found between polar molecules. So, polar molecule, the electrons are more stable. They're more close towards the polar molecule, but as I said before, but at least they're more fixed in this position. They're a little bit. They're not fluctuating as much, and this can only happen between a polar molecule because there's a partially negative. So this isn't the best example. I should show. That's more of a covalent bond. So that's saying should show more of a. If I was to show an intermolecular force of bromine here, and then say. Yeah. If this was H3. Right, if we're talking about intermolecular forces, right, this is more partially negative. So polar molecule partially negative. It has a stronger, because it's more electronegative. Remember what electronegativity is, right? Electronegativity is the ability of an atom to attract a lone pair of electrons within a covalent bond. See, this is in a covalent bond, and it has a strong ability to attract a lone pair of electrons, or it's not a lone pair, a valence pair of electrons, or electron pair, so I should say. It's the ability of an atom to attract an electron pair in a covalent bond. And this the electron pair here will be the valence electrons, right? And because it's more electronegative, it has a partial negative charge, partial positive charge, and it'll be able to attract the electrons on its carbon here, right? It'll be able to, it's attracting because it's so polar, so electronegative, and that's what's going to cause this bond here, this permanent dipole force. All right, so polar molecules. So hydrobonds, right? Hydrobonds only exist between some specific types of molecules. These intermolecular forces are stronger than induced and permanent dipole-dipole interactions. I like to think of hydrobonds as permanent dipoles on steroids, right? That's that. If I'm just being blunt, that's really what it is. They're just permanent dipoles to the next level, because permanent dipoles are just between two. It's just a very polar bond, right? But it's not polar enough to be considered a hydrogen bond. So a carbon bromine bond, it's quite electronegative. It wouldn't be classified as being. When I say polar means that there's a strong difference in electronegativity, right? So it's quite between bromine and carbon. There's quite a big difference in electronegativity, but it's not as big as a jump as in hydrogen bonding. Hydrogen bonding, there's only 3 atoms it's between hydrogen and 3 different elements. So hydrogen bonding is the name given to a very strong permanent dipole-dipole force. So dipole-dipole force, as I said before, is between 2 polar molecules, but this is a very strong permanent dipole-dipole force, because the severe difference between the hydrogen bonds and 3 most electronegative atoms. So it's the 3 most electronegative atoms. I'll go through them now, but so with some elements, hydrogen can form extremely strong dipole-dipole interactions. When these are strong enough to be considered a bond, it's called a hydrogen bond. So where are hydrogen bonds found? Hydrogen bonds are found when you have a hydrogen bond. So when you have a hydrogen atom bonded to either oxygen, nitrogen, or fluorine, because of the 3 most electronegative elements in the Pauling scale. So the most electronegative elements in the Pauling scale is fluorine, oxygen, and then nitrogen. I believe in that order. And I believe hydrogen is the least electronegative on the Pauling scale. I should have gone and checked, but that is pretty much the idea of it, right? If not, but at least the idea that hydrogen is very, very non-electronegative. It was a very low down electronegativity. Therefore, something that's very electronegative and something that's not very electronegative is a very strong difference in electronegativity. That's a very, very polar bond, and it'll be a very, very strong permanent dipole. So that hydrogen atom will form a strong permanent dipole-dipole interaction with another oxygen, nitrogen, or fluorine atom. Example of liquids with hydrogen bonds are water, hydrogen fluoride, ammonia, and DNA is example. If you do, you have to do it for chemistry anyway, but if you do it for biology as well, there's hydrogen bonding in DNA. But the one that you would generally see is within ammonia, water. But DNA, there's so many. There's three. There's oxygen, hydrogen, nitrogen, hydrogen. Actually, I don't think there's no fluorine actually. Scrap the fluorine, but it depends on your amino acids that you amino acids. I'm just getting that so wrong. So on your bases, don't say amino acids. On your base, depends on your bases that you have. Depends on the type of hydrogen bonding, but yeah, as you need to know that hydrogen bond is found in water, ammonia, anywhere that you can see that type of hydrogen bonding form with hydrogen and the three most electronegative atoms, which are nitrogen, oxygen, and fluorine. There will be hydrogen bonding. Why do hydrogen bonds form? When hydrogen is bonded to an extremely electronegative element, it develops a strong partial positive charge. A hydrogen is a very small atom, so it has a high charge density in this situation, and this allows it to form strong bonds with a highly partially negative charge. With a highly partially negatively charged atom. So let me give you an example, right? So water. This is exactly why water has such a high melting point, right? And you think it's 100 degrees Celsius compared to like other atoms, isn't it? So as I say, high melting point would be 0 degrees Celsius. High boiling point, 100. So sorry, I meant to say boiling point, not melting point. Even melting point to some extent, compared to other compounds, right? I'm going to use an example, right? So water has a boiling point of 100 degrees Celsius. To compare that to other molecules, other hydrocarbons, that's actually quite high because most of them got to to 60 or 70. They don't actually make it to 100 degrees Celsius. And melting point, most of these gases or most of these compounds, they melt way lower than 0 degrees Celsius. So what it is here, show you an example. And this is the reason why ice is so hard. It's quite you have to put a bit. You can't just kind of put your hand through it and break easily. You have to kind of punch it or break it away or chip it away. So how you'd represent, they'll ask you in the exam, right? They'll ask you in the exam how to draw the hydrogen bonding between molecules. I'm going to use water. I'll use two examples. I'll use water and I'll use an alcohol, right? That's the two examples that I can think of. They might even use it in DNA, but I'll do that when I get to the DNA video. I'll show you it. But I'll stop talking now and I'll actually get to the point. So and I have another let's go for here. Right. So how would I represent this, right? I should get a ruler. Should have got a ruler for this. But that is my bad. See, I'm not going to edit out this part of the video because I'm not bothered to actually edit this video properly and actually cut this out and do it. I'll just go and get my bag and get a ruler out, right? That's what we do here. Alright, so first of all, you need to give a charge, right? You need to show that this is a partially positive hydrogen atom, partially negative. Oxygen is partially negative. That's one. Just doing that is a mark in itself. And then when you do the body, it has to be a straight line. They will not give you a mark if it's a curved line. It needs to be a straight line, and it's a dashed line as well. It's not a solid line, right? Why does that not look straight? Some people like to do it out with the electron clouds. It's definitely the way I done it in my exam. That is a terrible electron cloud. Partially negative. Technically, this is a 2 partially negative because it's got 2 partially positives next to it, right? But in case, I think they won't be too fussy for not writing a 2 partially negative. You can just get away with saying partially positive or just saying partially negative, but technically it's a double partially negative charge. And there, and that is how you should you can represent it like that. You can represent it like that. I think you should represent the charge actually if you're gonna do it like that. At least show the lone pair, right? And that's your hydrogen bonding right there. You could also do it like if you're doing with a, let's just say methane, right? Say methanol. No, it wouldn't be to methane. Methanol. And then I don't care about this, but I mean. I should just throw CH3 there, but it doesn't really matter anyway, right? Could have this higher. Right, I can first of all, negative charge, partially negative, partially positive, partially negative, partially positive, and then showing from the bond here, from the lone pair to the atom, these are terrible charge clouds. First of all, make sure that they can't. They even in the mark scheme, right? They'll say these lines they can't cross over one another. So don't make sure that they don't cross over one another. You won't get the marks. Make sure that you get a straight line. That's another mark. Writing your charges. That's another mark. And writing and then showing your lone pair. That's another mark. It doesn't have to be the charge. You don't have to show it in the charge cloud. You can't just represent it like that. But at least showing you have the lone pair, that's another mark as well, and that's where they'll give you the marks. So they'll ask a question like show the structure of a methanol as a liquid, right, or something like that, and you have to show the hydrogen bonding. That's the most important part, and obviously make sure the structure of your compound is correct as well. All right. Remember the reasoning for this. The Russell reasoning for this: hydrogen is a very small atom, high charge density, partially positive atom. Highly partially positive atom and it will attract any highly partially negative atom, like a fluorine or an oxygen or a nitrogen. Hope this video is helpful, and that's it.